We're now going to prove that 3 points are collinear. If points are collinear, that means they all lie on the same straight line. And in order to prove that points are collinear, we need to draw a diagram. So very simply, we're just going to rule a straight line anywhere at all on our page, and we're going to put the position of the origin anywhere on our page apart from the line. So again, any sketch will do. So I'm just going to draw a line like that. There's no reason for me drawing it like that, just a random line. And then I'm going to put the position of the origin somewhere else on the page, like that. I'm then going to assume all 3 points lie on the line. So I'm going to let point A be somewhere on the line, point B at a different position on the line, and then point C at another position on the line, like that. So we are assuming they're all on a straight line, but obviously we'll have to prove that. We're then going to join all of the points to the origin. Like that. Now the moment we join all the points to the origin, we have formed 3 position vectors here. Remember, a position vector joins the origin to another point. So we need to put arrows in these 3 lines. And remember, position vectors are always directed away from the origin. Once we've put the position vectors on our diagram, we now need to get what they are in component form, and we do that by looking at the coordinates of each of the points. So to get the position vector OA, we look at the coordinates of point A. The x coordinate of point A gives you the I component of the position vector OA, so it's going to be minus 2i. And the y coordinate of point A is going to give you the j component of the position vector OA, so it's minus 4j. And we repeat, we do exactly the same to get the position vector of OB. So you look at point B, x coordinate is 1, so that means the I component is 1, so it's just going to be I, or 1i. And then the y coordinate of B is 5, so the j component of OB is going to be plus 5j. And again, put it in brackets to keep the I and the j components together. And then finally, to get the position vector OC, we look at the coordinates of C. The x coordinate of C gives us the I component of the position vector, so it's going to be 3i. And then the y coordinate of C will give us the j component of the position vector, which will be plus 11j. And again, put brackets around it. So we've got our 3 position vectors in component form. Now what we do is we get the displacement vector AB. So we look at the first 2 points that are in the line, and we get the displacement vector that joins them. So put the arrow running from A to B, that's our displacement vector. And what we're going to do now is get the displacement vector. So AB. Now, how do you find an unknown vector? Remember, it will always be the sum of the other vectors from its tail to its nose. So to get from the tail to the nose of vector AB, that's the same as moving along this vector and then adding on that vector. Now remember, if you move along a vector against the arrow direction, you need to make it negative. So AB is equal to the negative of minus 2i minus 4j. So we move along this vector, make it negative, and then we add on the remaining vector, I plus 5j. So the next thing we do is add the I and j components of each vector. So remember, multiply the I component by the negative here first, so that's going to be 2i. And then we're adding on another I, that's going to give us 3i. And then again, the j components, multiply this j component by the negative first, so that's going to be positive 4j. And then we're adding on 5j, that's going to give us plus 9j. So those are the I and j components of the displacement vector AB, and again put brackets around it to keep them together. We're going to do exactly the same now for the other 2 points in the line. We're going to get the displacement vector between point B and point C. So again, put the arrow direction on the diagram. So displacement vector BC. So again, to get an unknown vector, it will always be the sum of the other vectors from its tail to its nose. So travelling from the tail to the nose of BC, that's the same as going along this vector and then adding on the final vector. Now this vector here that you move along, you're going against the arrow, so you need to make it negative. So it's going to be negative I plus 5j. And then we're adding on the remaining vector. So once again we add the I and the j components. So multiply by the negative first. So we've got negative I and we're adding on 3i. So that's going to bring us to 2i. And then again deal with the j components. So multiply this j component by the negative first. That's minus 5j and we're adding on 11j. That's going to give us 6j plus 6j. And again put brackets around it. And those are the I and j components of the displacement vector BC. Now, once we've got the displacement vector joining the first point and the second point, and we've got the displacement vector joining the second point and the third point, we now want to show that these displacement vectors are parallel. So we want to show that AB and BC are parallel. So in order to do that, always start with the vector which has the bigger I and j components. We talked about that before in our notes. So we're going to start with AB. So write out displacement vector AB. Now, what we want to do then is we want to lift out a factor here outside the brackets so that the bracket becomes the other vector. So we want this bracket here to become the other vector, BC, which is 2i plus 6j. Now, what do we need to lift outside this bracket? In other words, what do we need to multiply 2i plus 6j by in order to get 3i plus 9j? Well, 2 times what gives you 3? Well, you're going to have to multiply by 3 over 2. Yeah, 3 over 2 times 2 is going to give you 3. And then 3 over 2 times 6 is going to give you 9. So to turn vector AB into the other vector, you would need to lift out a factor of 3 over 2. So what we're now left with is AB, displacement vector AB, is equal to 3 over 2 multiplied by the other displacement vector, which is BC. Now, what we've just done is we've shown that one vector is equal to a constant multiplied by the other vector, and that's how you show that two vectors are parallel. So therefore, AB and BC are parallel. Okay, now, here's how we now show that the 3 points are collinear. First of all, we've shown that AB and BC are parallel. Not only that, but B is a common point. So you think about it, if two lines are parallel and they have the same point in each of them, well then all 3 points have to be in the same straight line. Okay, so that's how we prove that the 3 points are collinear. Get the displacement vector between point 1 and point 2, get the displacement vector between point 2 and point 3, show that the displacement vectors are parallel, and if they are parallel and they both have the same point on them, well then all 3 points have to be in the same straight line. So that's where we are now. So since B is a common point, on both displacement vectors, and both displacement vectors are parallel, then points A, B and C must be collinear. And that's it. That's how you prove that 3 points are collinear.